Okay, I hope the PPT is visible. Okay, so in the last class, we were discussing about rigid registration, right? And one of the topics that we were discussing about was the ICP, or the iterated closest points. So in this algorithm, what you do is the main aim or the main assumption over here is that the objects that you are considering, let's say what we've considered is you have an image, okay? A 2D image which you can call as a source, and you have another image which you can call as the target, right? So in the source image, you have an object, and you're trying to map that or find the transformation of this particular object with that of this object, the same object in the target image. And what we are assuming is that the object which is present in the source image and the target image, okay, the basic shape of that object has not changed, or we call it as a pose consistency. Okay, that is a pose consistency, the location, the shape, etc. of these objects have not changed, is what we are assuming over here, right? Now, when you're doing a rigid registration, so under that assumption, so when you say rigid, the different operations or transformations that are involved are the scaling, the rotation, and the translation. So that what that means is, what you're assuming is the target image is a scaled, rotated, and translated version of the source image. So under that assumption, we try to find what is the transformation between these two images. Okay. And what we've learned is that so once you know what is a transformation, or once you estimate an initial transformation, you use the least square. It is what formulated as a least square minimization problem, right? So what we do is, for a particular pixel or a point which is present in the source, let's say you take what is the difference, okay, of that along with the rotated, scaled, and translated version of the source image. Okay, and you compare that with that of the target image, and you see what is the difference which is present. And depending on that difference, what you're trying to do is that difference would give us the error function, and we are trying to minimize that error function. So that is basically what is the least square minimization problem. Okay, and in the iterated closest points, so let us assume that these red color that you have here are basically the red dots are basically the source set. Okay, and the blue dots which you have here is the target set. So what we see here is that now there are blue points in T right here, which does not actually belong to the actual model distribution over here. That means there could be presence of outliers also, which are present in the target image or the target set that we are considering, right? Now, what is first done is an initial estimate is taken, right? So to find the initial estimate of the transformation, various methods can be applied. So in ICP, you usually take the PCA, okay, the principal component analysis, and then you try to register them together. So after the PCA, under the first or the initial estimate of the transformation, let's say this is how it looks like, okay, where you have the source set, okay, and the target set, which are kind of aligned together. Now it is not a perfect alignment, right? Now this is the initial estimation. Now what is done is, in order to refine this, the iterated closest point will try to find out the closest point for each of the points in the target, okay, with respect to the source. So while finding that there is a kind of a one-to-one correspondence when you're trying to find this closest point of each of these point pairs. Okay, and what happens is that eventually the outliers would be discarded, the ones which are there further away. So what is done is, once the correspondence between the pixel pairs are determined, the distance is calculated, right? And then depending on this distance, there is again a least square minimization done, okay, with respect to the transformation, and the next transformation is and then it goes as the next iteration. Again, the distance after that transformation, the distance is again calculated, and so on. So this repeats for various transformation, for various iterations. And then finally, at some point, or after some iterations, what happen is that you will get the score, okay, or the error function value, less enough, okay, or at an acceptable level, and then you can see that it is kind of aligned together or registered together with all the outliers being discarded. So this is basically the iterative closest point algorithm. And what we saw is, apart from this approach, you also have so in ICP, what you see is that there is a point-to-point correspondence. So if you have a target, a point from the target and a point from the source, you're assuming the closest distance between these 2 points, and it's a one-to-one, a point-to-point correspondence. So instead of going for that, now there are many cases where just as we saw in the previous example also, you may not have exactly a one-to-one correspondence there, okay? So sometimes it is better, rather than going for a point-to-point correspondence, it may be better to go for a group of tokens, okay? And we can call these as frame-bearing group. So what that means is, for each of the transformation that is identified, or for either of the transformation that we are considering, okay, instead of taking only points into consideration, we also take some other geometric primitives also along with it, in order to find or estimate the transformation, okay? Like for example, as an example, it could be a line and a point together, okay, for the rigid registration. Or if you take the case of rigid and scaling, we can say it's a one line and one point of the line, that is, which is not present in the line, and so on. So the frame bearing groups for 3 of the transformations are shown here, and this is for the case of 2D to 2D transformation. If you're considering the frame bearing groups for 3D to 3D transformation, is just different. Okay, so what you see is that for the 3D to 3D transformation, here, instead of 2 points over there, it becomes 3 points here, and so on. So in this case, it would be 2 intersecting lines, okay, that also comes in between, and so on. So the frame bearing groups for each of the transformations, knowing which frame bearing groups support which all transformations in 2D to 2D registration, as well as 3D to 3D registration, is important. Okay, now what we need to discuss is, what if you have multiple correspondence between source and target? Okay, that means like for example, if you're taking the case of let's say the ICP algorithm itself, okay, so there you have target over here, okay, and let's say in the source you have 3 points, okay, which are all of which are equidistant, let's say, okay, so let's say these 3 points, all the 3 points are equidistant from this target here. Then how does it take which one is the closest point? It can be any of these. Okay, so that means, what if there is multiple correspondence between a point in the target image with the with the points in the source, or the transformed source image, which is basically G, right? So if you want to find this, now what we can do is, an approach that can be followed here is, you can use a ransack like algorithm here. Okay, so ransack, if you remember, what it does is, it is basically used to identify the outliers. So it randomly chooses a few points and then tries to calculate what is the error function there. Okay, so similar concept is done here. So that means what is done here is, first you are selecting a frame bearing group, okay, for the source and the target. Okay, so that frame bearing group, it can be 2 points, it can be a line or a point, etc. So let us say we are taking 2 points itself as a frame bearing group in this case. Okay, so it can be any frame bearing group. So first it is a frame bearing group is selected randomly. Now that is the more important point over here. It is taken at random. Okay, so at random you choose. So for example, let me assume that I'm choosing this particular point and randomly. So let's say you have a set of points over here which are equidistant. Okay, we are randomly choosing one of that. So let's say I'm choosing this particular point over here, right? So randomly I choose this. Okay, and then what I do is I try to find out what is the correspondence between these two over here. Okay, so what I'm saying is I'm saying that okay, these two are the corresponding points. Okay, and to this let me apply the transformation, or let me compute the transformation with respect to these 2 points over here. Okay, and that particular transformation, okay, is then applied to the whole source image, and then that transformation is compared with that of the target, okay, using the least square minimization. And so from there what you do is you kind of get a score to say how similar, or how similar the transform source is with respect to the target. Okay, so you got a score corresponding to one random pair that you have chosen. Okay, and then in the next iteration what is done is, again, it's a ransack like algorithm, right? So the next iteration, again another point is randomly selected, and then from that point the transformation is calculated, and then this transformation which is computed is applied on the source. Okay, and then from the transform source it is being compared with that of the target, and then the score is calculated on how similar it is. Okay, or basically it's like an error function itself. So for each random cases, or for each random correspondences that you have, the score is being calculated, right? So each time you have the score, what you do is, now the one with the best score, or the transformation corresponding to the best score which you got, okay, would be taken as the final transformation, and we go ahead with that transformation. Okay, so this kind of an approach, okay, it's like the ransack approach which we have learned earlier, and that is done when you have multiple correspondence between the points in the target as well as the source image. Okay. So here, this is an example where it shows image mosaicing, okay, or building image mosaics. So mosaics means nothing but, it's like as if you're taking multiple images and stitching them together to form a bigger image. Okay, so that is what you call as mosaic. Now, in image mosaic, or trying to create an image mosaic, it is very important to register the images. So all these registration techniques would help a lot, or it can be applied for image mosaicing. Okay. So in image mosaic, now if you look at these images over here, what we see is basically it's the images of an airport, right? But you have different sections separately. Okay, so if you are able to try to register, and find out which are the images which are kind of continuous over here. Okay, if you are able to register these together, then you would be able to form the bigger picture, as you see over here. Okay, so this is the result after the registration, and this result has been formed, okay, from such inputs which have been taken. So what is done is basically registration between all these images. So first what we do is we try to estimate the transfer. So we take, let's say, any two pair of images from here. Okay, so one acts as a source and the other acts as the target over here, and then we try to kind of estimate what is the transformation between these two images. Okay, and then depending on that we try to align them together and then stick them together. So what you'll see is that, okay, since you have these kind of images, it might be just a small region over here and a small region over here which kind of corresponds together. Like if you look at this case over here and this case over here. Okay, so we try accordingly, the regions are registered and they are stick together in this sense. You just overlap these regions which are common, and then that forms a continuous image, right? So like that, for all the multiple images you do the same, and then you get the bigger picture. Now another example is shown over here. right? So in this example, we actually, we can actually, so here what we see is the plane is actually moving, okay? So this is also for an airport, but in this case, the aeroplane that you see over here is actually moving, right? So when you try to register this particular kind of images where the background remains the same, but the object is moving, okay, what we're able to find is, an example is like this, where you can see the aeroplane moving in all the images, okay? It's the same plane over here. That is basically you're trying to, you'll be able to find what is the trajectory of the aeroplane, right? So this is another example of how you can apply image registration, okay? But the basic concept is the same, where you take different images together, and then you try to, register. That is, you try to find the transformations, okay, with respect to this bigger image plane, and then you, register them and stick them together to get this image. Okay. Now, say we have two images, okay, and we want to stitch them together, right? So what we do is we first, we can find what are the tokens which are present in the image. Okay. Now, what you mean by tokens is, some regions of interest. It need not be regions exactly. Some geometric primitives of interest. Okay, that is one thing. It may not be always geometric primitives. It could be some kind of, features also which are present. Okay. So what we try to identify is what are some specific characteristics of the image, okay, that can be used for registration. And some examples are to find the interest points or the key points, okay, or you can compute the SIFT features for finding the neighborhood, okay. You can also use the gradient to find the edges, okay, or you can also use edge operators to find the edges, okay. So all these are, you can call that as the tokens, or you can say finding tokens. So tokens means basically points or lines of regions of interest that we have, okay. I can't exactly say regions of interest over here. What I mean is some kind of features, some kind of characteristics of the image which are of interest, okay, or which stands out. Those can be considered as tokens, okay. So first what we do is we find these tokens, okay, and then these tokens, we find what is the correspondence between the source image. And so if you have the source image over here and you have the target image, the same tokens, whatever we are considering, okay, is found from this image and this image. And then we find the correspondence between these particular points corresponding to the tokens, okay, in the source image and the target image, and you find the transformation. So the rest of it is the same, finding the correspondence, okay, estimating what is the transformation, okay. Now we do not know what is the kind of transformation over here, right? Okay, we cannot say, or we do not, we may not, we cannot always say that it is a rigid registration, okay. So it may not be, we can, if we are not sure what kind of a registration it is, in the sense if the object is rigid or not, okay, in the broader sense, if you're not sure of what is the type of transformation, okay, if you're not sure if it's a Euclidean transformation, we can try to, or we assume it to be a projective transformation, okay, because as we know, projective transformation actually forms the bigger picture, right? Under projective transformation you have the affine, okay, and under that you have the Euclidean, right? So when you say projective transformation, it is inclusive of the affine and Euclidean transformation, right? So in general sense, we can assume that the transformation which happens between the source and the target over here, okay, is the projective transformation. And since we are doing now here, this what we are considering as a 2D image, here also we are talking about 2D to 2D transformation, right? Or 2D to 2D registration. So so what we can say is it is basically called as a plane projective transformation. Okay, plane projective transformation, plane because it is basically dealing with images. And another name for this is homography. Okay, so let us say we have two images, okay, and we have images I1 and I2 over here. Okay, and what we need to do is we want to find out what is the projective transformation or plane projective transformation which exists between the images I1 and I2. And we know that for a projective transformation, we can write it as x dash is equal to hx. This is something which we've seen earlier, where this h is the projective transformation matrix that you have. Okay, x is the point, okay, before the transformation, and after applying the transformation on the point x, what we get is basically x dash. Okay, something which we have already discussed. So the same concept can be applied over here also. I can write it as x2 is equal to hx1, where x1 is basically a point in image I1 and x2 is a point in image I2. And remember, because it's a projective transformation, what we are doing is we are expressing this in terms of homogeneous equations or homogeneous forms here, right? Now, so we can write it as x2 is equal to hx1, okay? And this particular H matrix, okay, that is the projective transformation matrix that we have, okay? So what we are trying to do is, okay, let's assume that we have already found out what is the correspondence between x2 and x1. That means we have found out that for the let's say image I1 and this is image I2, I have some point here, this is x1, some point here which is x2, okay, and I have found that this x1 corresponds to this x2, okay. So after you know what is the point pair correspondence, you can apply this particular equation to find out what is the transformation or the projective transformation. Now if I'm writing this in let's say the equation in the matrix form, I can write it this way, okay, just trying to express this as a matrix form. So here what you see is x2 and y2, right? These are the coordinates of the point which is present in image I2. And then here what we have is this hx1, okay, which has been expanded. So I can write it as h11 x1 plus h12 y1 plus h13 divided by h31 x1 plus h32 y1 plus h33. So here this term that you see, okay, is corresponding to x2. That means the x coordinate of the transformed point or the point in the I2, and this one corresponds to the y coordinate of the point in I2. Okay, so now that we have this equation, what we can do is we can solve this further to find a system of linear equations, okay, and we can solve this to find out what are the values of the projection matrix, or to basically find out all the elements of H, and basically to find out what is the transformation. Okay, so we could do that, or we could have done that, but one problem over here is that if you're taking a real case where you find these points, okay, we may not be able to find an exact correspondence between two points. Okay, that means for a particular point we may not be able to find an exact corresponding point over here. Okay, now that may happen, right, if finding all these points is coming as part of some image processing technique. Like for example, you initially had let's say I1 and I2, okay, and you're applying some kind of image processing technique. Let's say you're finding the gradient, or you're using some kind of edge operators to find, okay, and whatever is the gradient that you got, okay, let's say those edges you're considering it as the different points over here, and correspondingly you have it over here also. Okay, so sometimes when it is coming as a result, when all these frame bearing groups are identified as a result of some image processing techniques, prior image processing techniques, okay, what you get may not be exactly perfect. There might be some errors, there might be some noise in the image. Okay, now so since you have that noise or presence of maybe more than multiple correspondences, etc., so what happens is that, okay, you cannot exactly get an equation where you can equate it to 0 as such. Okay, so the system of or solving using a system of linear equations, okay, would be difficult. It is not possible with real case with images. Okay, especially when you have points which are coming as a result of some kind of edge operation or gradient operation or so. So what do we do when it comes like that? Okay, so if we cannot assume a one-to-one correspondence, okay, what we can do is instead of taking it as a system of linear equations and solving it, you can formulate that again as a minimization problem. Okay, so what we do is we try to find out what is the error function. Okay, by trying to see what is the difference in the transformed matrix or the transformed points. Okay, so let's say this is a transformed point over here, the x coordinate of the transformed point, and this is the x coordinate of the target, right? And here, so this one I'll write it as g. This is the corresponding the point, okay, a transformed point of g in the y coordinate, and this is corresponding to the y coordinate in the target. Okay, so what we do is we try to find out what is the error in the x coordinate. Okay, square that, and then we try to find out what is the error or the difference, okay, between the transform values and the actual target value in the y direction or y coordinate, and then square them together. Okay. And then this one you're doing for all possible points which are present in G. Okay, for all the points which are present in G, you're trying to do this. So, and so this particular function, whatever you have here, this particular summation error summation function, what we do is for each iteration, we try to minimize this. So we basically formulate this as a minimization problem in the real cases that we are considering. Okay, so in the previous case, right, what we considered was finding the transformation of two images and doing an image mosaic. Okay, when you have two images. Now, what if you have more than two images? Okay, how do you do for multiple images together? So when it is two images, it is very easy. You just have source and target, and you just try to find out what are the corresponding points between these. Okay, and then um, we try to find the correspondence. Okay, just give me a minute. Okay, sorry for that. Let's continue. Okay, I hope the PPT is visible. What we were discussing was what do you do when you have multiple images or more than two images? How do you exactly go about with finding the image mosaic? Okay, so what we do is so let's say I have three images here. Okay, so let's say I have I1 here, right, I2 here, and I3 here. Okay, and I have three images, and I'm trying to find what is, or I'm trying to stick them together. Okay, and what we saw earlier was that since you have a source image and a target image, what you do is for the different points which are present, okay, we try to find out what is the correspondence between these 2 points. Okay, so basically you're find out what is the transformation with respect to that. Now, in this case, since you have three images, what you do is I need to find out what is the transformation which exists between these two images. I need to find out what is the transformation which exists between image 2 and 3. Okay, and I also need to find what is the transformation with which exists between the first image and the third image. That means we need to find out, if you have multiple images over here, you need to find out the transformation which exists between all the three images. Now, why we try to find out between I1 and I3 is because basically for image mosaicing, all these images form as part of a bigger picture. Okay, so let's say this is the bigger picture that you have here. Okay, this I1, I2 and I3 may be some, it might be placed over here, just as taking an example, right? So all these images, since they form a part of the bigger picture, okay, it is important to compute all the transformations, okay, together. Okay, in the sense, we try to compute all these transformations with respect to the same reference plane or the reference coordinates. Okay, since you have this as part of the bigger image. So this technique in which we try to find out all these transformations, okay, using the same reference coordinate, okay, is what you call as a bundle adjustment. You call it as the bundle adjustment. And this concept is something which is important when you're dealing with 3D reconstruction also. Okay, so what we do here is we first try to find out what is the reference coordinate, okay, whichever is the reference coordinate that we are assuming, and then we find these transformations T1 to T23 and T13 with respect to this particular reference coordinate that we have taken or assumed. Okay, so let's go to the mathematical details over here. Now, this particular equation, okay, this is the equation that we are trying to minimize. Okay, so in this equation, what we see is that there are terms. Okay, each of these terms stands for each of the transformations. Okay, so this particular term that you have here, or this particular row that you have here, corresponds to what is the, sorry. Okay, so this particular row, what you have here, right? It corresponds to basically the T12 transformation. Okay, so as I said earlier, you have I1, you have I2, and you have I3. Okay, so this is going to be my T12, this is going to be my T23, and what we have here is basically going to be my T13. Okay, so this particular equation, it corresponds to T12, this corresponds to T23, and this one corresponds to T13 here. Okay, now let's discuss what each of these terms actually mean. Now, if I say T21, okay, what I mean by that is I'm transforming the points which are present in image 2 and I'm mapping it to the points which are present in image 1. Okay, so in this particular term, when you see this particular term, what this means is I'm transforming the points, okay, which are present in the image 2, and I'm mapping it to the points which are present in image 1. Okay, and then after applying this particular transformation, okay, I'm finding the difference, okay, between the transformed points with respect to that of the target image, okay, and I'm trying to calculate what is the error, okay, between each of the points which are present. Now that one I'm going to do for all the point pair matches which are present. Okay, so that will give me that summation over here would give me the transformation or whatever is the error function or the minimization function with respect to these two images, which is I1 and I2. Similarly, I can do for I2 and I3. That is, I can find out what is the corresponding minimization term for T23 transformation. That is between I2 and I3. So to find out for T23, what I do is if I look at this equation here, T31 means the points. Basically, I'm transforming the points which are present in the image I3 and mapping it to the points which are present in I1. Okay, and then these transformed points, this transformation, I apply it to the source image over here, and then I try to find out what is the difference between the correspondence in the first image, image 1, and the transformed image 3. Okay, and again I try to find out what is the error function. Okay, and that gives me T23. Now for the next term which you see, it is basically T13 transformation. That is, you're trying to find out what is the transformation between this I3 and I1 here, right? So in this T13 over here, okay, sorry, this is supposed to be T13, okay, because I'm doing basically I'm taking 1 and 3 matches. This one here, this is basically T23. Okay, so I'm trying to find out these two over here. This is basically T23 because I have 2 and 3 matches over here. Okay, so in T23 transformation, what I do is I could have taken it as just like how I denote it in this form. I could denote this also by saying that, okay, I'm taking xj1. Xj1 becomes xj2 in this case. Okay, and then I'm just trying to find out what is the transformation over here. I could have written it as t2 mapping to 3, and then xj2 and so on. But instead of writing this way, I'm writing it in this form over here. That means I'm writing this particular term in terms of this T2 to 1 transformation, and this matrix which is given over here, T3 to 1 transformation. So why I'm doing that is because, okay, I can, so this is basically a transformation where it maps to image 1. This is also a transformation which maps to image 1, right? So if I'm making use of, or if I'm able to express this transformation T23 in terms of, okay, the transformations which maps to image 1 itself, okay, that means the basic reference frame which I'm considering, or the reference coordinate which I'm considering, is with respect to image 1. Okay, so for all the 3 terms, the basic reference which I'm doing, because the mapping which I'm doing is basically to image 1. Okay, so that means the reference frame remains the same. So it's because of that that we have put the third term in this way. So when we are now trying to minimize this whole thing, what happens is it is basically with respect to the reference frame of image 1, right? So all the 3 gets minimized together in the same form. So what happens is when you're trying to find the image mosaic of the bigger picture, right, it gives us lesser error and a better transformation computation or estimation, okay, in this case. So this whole equation which you have here is basically your minimization equation, okay, which incorporates all the 3 transformations, which is T12, T13, and T23, okay, and all these transformations are expressed with respect to mapping to image 1, okay, so that forms the basic reference plane that you have. Okay, and this process which you see here, okay, this kind of approach is what you call as the bundle adjustment. Okay, so if you look at this bundle adjustment, you see that the concept is easy. Okay, all that you do is you choose a particular reference frame, okay, and then you express all the transformations between all the different images with respect to that reference frame, and then you formulate the minimization problem, okay, accordingly. Now, when you're, one limitation in the case of the bundle adjustment is, okay, what if you have a lot of images? Now, we took the case of 3 images and we saw how many terms, there were 3 terms for the minimization function, okay. So if you have more images, as the number of images increases, what happens is the transformations which you have to find. So now, as we know, the transformation is found between each of the images, right? Each of the pairs of images which are present. So if the number of images increases, what happens is that the number of transformations which we have to calculate also increases. Okay, so finding so when you have these multiple terms, okay, for the minimization function, try to find out the best set of transformation matrices, okay, which would give us the best optimal solution is going to be very difficult when you have a large number of images, okay. And that is one limitation of the bundle adjustment problem, okay, because it becomes a complex computational problem in this case. Now coming to image blending output, okay, so let's say you have registered some images. So in this particular example, okay, there are 80 images which were present, and these 80 images were registered together to give us the image mosaic, okay. So what we say is that when you immediately try to register these images and then form this larger picture, okay, you see these boundaries over here, right? Okay, so there is these presence of boundaries, okay, which are very evident in all the images, and that is something which is not required, or which we do not desire in our image, right? So after this registering, we also go for some kind of a blending approach, okay, that is a post-processing approach to make it look better, right? And in this blending approach, what is done is, now you can use various approaches for this, okay. One very simple example, what you can do is, at these boundary pixels or boundary neighborhoods, we can simply calculate what is the average, okay. So by just averaging it out or smoothing it out, you can reduce this effect of this presence of boundaries between images when you're doing the image mosaicing. And there are also other techniques, okay, where you can blend the different images when you're going for this kind of image mosaic, or let's say the panoramic view or so, okay. There are different approaches. Just one simple approach which you can do is just smoothing it out, okay. So remember that along with image mosaicing, or image in an image mosaicing operation, or that process, what you do is, after registering the different images, you also go with, you need some post-processing technique like a blending approach, where you try to reduce the presence of these boundaries which are present and give us a more realistic view, as you see over here. Okay, so so far what we were discussing about was the registration techniques, okay, when both the source as well as the target image, or target source and target set that you have, are in the same dimension. That is, like, for example, if you're doing a 2D to 2D registration, okay, or if you're doing a 3D to 3D registration, okay, so that's the only topics which we saw. So basically the principles would be same. If you're going for a frame bearing group, the type of groups which are, or pairs of frame bearing groups which we consider would be different for both the cases, but the basic approaches are the same, okay. So as long as the dimension of the source and the target remains the same, okay, all those techniques would apply. Now, what if the source and target which we are considering are not in the same dimension? Okay, like for example, let's say I'm doing a 3D object to 2D image registration. That is, I have a 3D object, okay, in the real world, and then I'm taking or let's say I'm considering an image of this object, okay, so that gives me the 2D image over here. So my source is going to be a 3D object, and my target is going to be a 2D image of this particular object. Now it may not be a direct actual image of this. It could be a transformed, scaled, rotated version of the object which is present as the image, okay. So as for example, you can just consider this image which is shown over here. So let us say this is the particular model, or model basically means this is a particular 3D object that we are considering, okay. So in this particular 3D model, okay, you have applied some kind of a transformation where there is some kind of a rotation, translation, or scaling operations which has happened, and then you have imaged it, and this is the kind of image that you have obtained, okay. So what you're trying to do is you're trying to register this particular 3D object which forms my source, okay, to the 2D object which is my target here. So this is the 2D image and this is the 3D object. So in such cases where the source and target does not have the same dimensions, okay, the kind of registration approach that we take would be a little different, okay. So what we do, a little different but yet similar, okay. So what we do is first we try to find a frame bearing group, okay. So it could be points, it could be lines, etc., okay, and then you try to estimate what is the transformation, okay. Now once you have the transformation, you are applying the transformation on the source object. Now in this case it is no longer an image, it is an object. You apply the transformation on the 3D object, okay. Now if you want to find out what is now, what we do is in the previous cases what we did was since source was an image, okay, from the source image you do the transformations to get the transformed image which we call as G, and then you do a comparison with the target image. If this is a target image, okay, you try to do a comparison between these to find out how similar these are, okay. So that was the approach that we took earlier. Now, in this case, since the source is no longer an image, okay, but it is kind of a 3D object, let's say, I'm applying a transformation, okay, and I get some kind of a 3D object over here also after the transformation. Now, in order to do the comparison, since you can't directly do, because this is a 3D object and this is a 2D image, what I do is I take the image of this one, okay, or the projection of this one, okay, and then that image I compare it with that of the target. So that is the only difference you have here, okay. So what we do is after we do the transformation to the 3D source object that we have, we take the image of the transformed 3D object, okay, and that image you will compare it with that of the target image. So that means at that time when you're taking the image of this one and then doing, then it would be basically a 2D image to 2D image comparison that you have, right? And then you try to find how much is the similarity as a score, okay? And those transformation which gives us the best score over here, okay, would be the final transformation. So it's again an iterative process that you have. Okay, so as I said earlier, here you have the 3D structure which is basically the source, okay, and I have here which is the target, okay, and basically it's the 2D image. And these yellow lines that you have here, it is actually the result, okay, which has been overlaid on the image, okay. Now, so what we do is that for the source, yeah, the tokens that we are considering, okay, would be with respect to that of the 3D object, okay. And for the target, the tokens that we will be considering would be with respect to the 2D image, okay. So that would be different, whatever is the tokens that we are considering, okay. So that's one point that you need to remember. Okay, so let's now see how we go about this step by step. Okay, we've already discussed this once. I'll just say this again. So what we do is, if we know that a specific line in S, okay, maps to a specific line in the target. So this source is 3D now, okay, and this target here is my 2D image. Okay, so let's say that I know that a specific line in the source maps to a specific line in the target. We can use this information, mapping information, to find out what is the transformation which exists between the source and the target, right? Now, this particular transformation which we have estimated, okay, we can apply that to the source object, okay. And as I said earlier, what I said is that we would try to take the image of this. Okay, so how we do that exactly is, right, we assume that we have a camera model. Okay, so there is a specific camera model which has got, whose intrinsic and extrinsic parameters are known to us, and we have a camera model, right? Now, using this camera model, we try to find out the image, or we try to take a 2D image, okay, of this particular transformed source object that we have, okay. Now, this particular method of using the camera model to take a 2D image of the transformed object over here is what we call as rendering. Okay, so we what we say is we are rendering the transformed object model. Okay, and what this rendering, what it gives me is basically a 2D image. Okay, this gives me a 2D image, and this 2D image I can compare it with that of the target to give me what is the error function which is present, or what is the score of the estimated transformation. And for the next iteration, what happens is, depending on this score, the transformation here changes, and accordingly, again, it is recalculated to find the error, and you try to minimize this. Okay. Now the challenge here would be, how do we get a good score? Okay. So let's take an example over here. So in this example, model, okay, refers to what is the 3D object. Okay, so this is basically, I'll write it as the source, or this is basically the 3D object that I have. Okay, and this is basically only one particular view of the 3D object. Okay, now this is my input image. Input image, I can call it as the 2D target image. Okay, now what I'm trying to do is, I'm trying to, or I want to register between this object and the input image over here. Okay, that means I want to overlay and see how this 3D object can be overlaid on the image. Okay, so that is what you see over here, which is basically overlaid. So what do? Is we first try to identify tokens, okay, in both the image, as the source as well as the target, right? So these tokens, it could be these lines, it could be edges which are present, okay, it could be these circles, the geometric primitives that you have, and so on. So first we try to find the tokens, and when you try to find the tokens, we remember that these are with respect to the 3D object and the tokens with respect to the 2D object. Okay, now once you find the tokens, what you do is you're trying to find, okay, what is the correspondence between these two, right? And then we calculate what is the transformation, just as discussed in the previous cases, and then we try to formulate the minimization problem. And finally, the how we have the output, okay, is as you see here, where the 3D object, okay, whatever was a 3D object here, the transformed version of the 3D object that gave us the least minimum value for the error function, okay, is this particular mapped. So that has been, that particular model or transformed source has been mapped or overlaid on the target image, and this is the output that you see. Okay. So the remaining regions, these regions where it does not cover, these basically form as outliers, or regions which are not of interest for us. Okay. Okay, now how do you compare the transformed and the rendered source to target? Okay, so, or how do you compare the matching between the source and the target? We'll see that. So what you do is basically you're trying to find out some kind of a scoring function over here, right? So the scoring function, to find the scoring function, you can use different imaging, quantities. That is, either you can use tokens. Tokens in the sense, let's say you're identifying some corners which are present. Okay, you're trying to identify certain edges which are present, and then you're trying to see how many of these tokens actually overlap, and so on. Okay, so that is one way in which you can try to see how much is the score. Okay, or you can create a scoring function, or it can be with respect to texture, in the sense you look at the texture of the source and the texture of the target, and you see how much the texture is similar to each other. So that's another way of formulating the scoring function. Or another possibility is where you use the pixel intensity. In pixel intensity, what it means is, okay, you just try to see for a particular pixel value, okay, is it the same pixel value in the source as well as the target. But this particular approach where you take the pixel intensity for the scoring function is hardly used. The reason why it is hardly used is, let's say you have a source object that you have, okay, a source, and you have a target, okay. Even if it gives the exact same view of the object, okay, but let's say this is on a lighter side, okay, and this is a darker picture of the same, okay, even if it is exactly same and the correspondence of the mapping of the transformation has been found and it is exactly same, since this is a lighter version in the sense, it would be the illumination is different, okay, that's what it means, okay. So this has got a brighter illumination, whereas the target has got a darker illumination. Let's assume such a case. So in such a case, what happens is that if you go for a pixel to pixel comparison, okay, it will give me the score would be very less over here, or it would say that the similarity is very less, because this gives me a higher or a lighter pixel intensity value as compared to this particular pixel, okay, because of this illumination variation. But in actual case, if you see, these may be images where it's the exact same images of the same object, but it's only different illuminations. So that is why the pixel to pixel comparison is rarely used, unless and until there is no illumination variations which are happening. Okay, so if there are, since it is prone to illumination variations, okay, using pixel intensity as a scoring function, or as finding to find the errors is rarely used. Okay, so another important method by which you can compare the two source and target image is by using, or is rendering the silhouette of the image or of the object, okay. So in this particular technique, what we do is, okay, we first find out what are the silhouette edges which are present on the image using the camera model, okay. And then we try to, so what that means is we remove whatever intensity is present. So let's take, for example, this particular image, okay. In this image, it is image of an aeroplane, and let's say you did have, some appearance, okay. So this was basically, some colors were there, or some variations of grayscale was there, okay. And let's assume this was the image that we have. So when you're using this technique, what you're doing is you're getting rid of any of the intensity which is present here inside, or any of the texture which is present inside, and so on, okay. So all that we are concerned about is this basic boundary that you have, or the edges which are the basic, main edges or boundary that you have in this particular object, okay. And these edge points, whatever is obtained, okay, can be compared with that of the target image. So what that means is, instead of going for exactly the same object, okay, we just try to get rid of all the pixel intensity values and just take the edge information alone over here, and then we try to find out what is the overlap between the source and the target, okay. So if we say that there is a maximum overlap between both, okay, then we can say that the matching or the scoring function is high enough or good enough, okay. So this is another approach that we can go with. But in this approach, you have certain, limitations, okay. So if you look at this particular figure, like for example, in this figure, what we see is, this is the particular 2D object, 2D image that you have, and you were trying to superimpose or overlay, okay, the transformed source object on this, okay. Now we know, now this particular spanner, we know that it is present over here, okay, but then it has calculated it like this over here, okay. Now one reason for the error that could that has occurred because of what has occurred is because if you look over here, the background is not exactly a uniform kind of background. Okay, you see that it is a very noisy background, and because of these noisy background, what happens is you do have certain black pixels that come into picture in between. Okay, so that kind of gives us that underlying pixel intensity gives a kind of a false boundary effect. Okay, because of which the algorithm is trying to it is identifying these as edges. Okay, basically these are false edges. It's just noise over here, but it is identifying these as edges, and then it is trying to find the transformation, and this is kind of the mapping that has been obtained. Okay, so what happens is, even though you know that there is no object which is present over here, okay, this particular transformation, or this particular overlaying, okay, shows us this kind of result with a very good matching. The reason being that, okay, the texture which is present below these white borders that you see here, okay, have got some kind of slight changes in the intensity, and because of this it is identified as false edges, and you get a high matching score. So sometimes, such false identification of the borders also causes, or some errors in this particular approach. So we need to be careful, okay, when we are trying to use this. Okay. Now going forward with deformable registration. So far what we have discussed was about registering the rigid objects. We saw how we can register the rigid objects in 2D to 2D. We saw the 3D to 3D case. Okay, it's just an extension of the 2D. And we also saw from 3D to 2D, okay, how we can use a rigid registration. Next, what we'll see is how you can register deformable objects. So deformable objects means, if you remember in the one of the first classes which I've discussed, okay, in rigid registration, what we assume is that there is a pose consistency of the object, or the object has not changed its shape, okay, when in all the multiple images that we are considering. But in the case of deformable objects, what you assume is that the object has deformed, okay, over a period of time. That is, when you're trying to image the same object, after some time the object has changed its shape. So such kind of objects can be called as deformable objects, and registering such deformable objects, such techniques, okay, would be different from that of the rigid, because the basic assumption of the rigid registration does not hold here. Okay, so such kind of registration approaches which deals with deformable objects can be called as deformable registration. Okay. Now, some examples, okay, where you can find such deformable objects is in the case of medical imaging. Okay, that is, when you're trying to image any human organs, okay, you see that there would be some kind of change in the shape of the organ, either in the shape of the organ, or at least there might be some kind of a patient movement also that can cause the change in the position of that particular object. Okay, and most of the organs, like for example, if you're considering the heart, the lungs, etc., all these would change the shape, okay, as and when we are imaging it multiple times. So each time you take, okay, you know that it is not exactly the same as the before. So in medical images, you see that the registration that we would be dealing with would be the with respect to the deformable objects. And the concept of matching using tokens, okay, it is valid only if the object is rigid. That is what we have discussed till now, right? So if there is a change in the objects which is present in the source and the target, then that means we cannot find the correspondence points at exactly, because the object has changed its shape over here, so we cannot find an exact point to point correspondence in this case. Okay, So that is why we need to go with special techniques which are unique to deformable objects. And so here ransack, it cannot be used, okay, because it assumes because we cannot have that exact point to point correspondence here. Okay, so before we go further with the registration techniques here, just a basic, concept that you need to learn is the barycentric interpolation. Okay, so let us discuss what is this barycentric interpolation, and then we'll see how we can apply that to, or how it helps with the image registration of a deformable object. Okay. Now, when I say interpolation, okay, in image processing, what that means is you're trying to find out an average between the pixel intensities which are present in a particular region, okay. And like for example, let's say you have a particular region over here, okay, and you have a particular a pixel over here, a center pixel value whose value we need to find out. So what we do is we basically look at the neighboring pixels or the neighborhood, okay, and try to kind of find an average value in order to get the interpolated value over here, right? Now this averaging, it can be a normal averaging, it can also be a weighted averaging approach, okay. So basically what interpolation means is it is kind of a weighted average that you take between different points in order to find out the value of a unknown new point that you have, okay. So first, to know how this is done, let us assume just a one dimensional image in the sense, let's say you have only a row vector or a column vector as an image, okay. Then we'll go to a 2D image and see how that is done. So let's say you just have a row vector or a column vector, and let's see how we can do this barycentric interpolation. So let us assume you have 2 points, x1 which corresponds to image 1, and let's say you have x2 which corresponds to image 2, okay. And the intensity, pixel intensity value of this point or pixel x1 which is present in the image 1 is basically red, and the pixel intensity value which is present in the pixel x2, okay, in image 2, let's say it is having an intensity blue, right? Now let us say you want to find out what is the pixel intensity value at this particular point T that you have, right? And this T, if you see, it is this location of T, right? T is located somewhere in between x1 and x2, okay? And I want to find out what is the pixel intensity value which is present over here, okay? So in this case, what we do is we know that if this point T over here, okay, if this point T is present close to x1, that is over here, right? If the position of T is present close to x1, I can take the value as red, or if it is equal to this particular point over here, it becomes red. And if the value of T is somewhere over here, if it is equal to 1, it is present over here, then it becomes blue, or the value or the pixel intensity value is blue. And when you take any other points in between, it would be a weighted average of the red hue as well as the blue hue, or the blue red and blue intensities, okay. So that means if I take a range from 0 to T, this is a value for T is equal to 0, okay, this is a particular position x1, right? And for T is equal to 1, this is a particular expression x2. So at T is equal to 0, it will get the intensity of x1, and as it moves away or further from x1, what happens is more and more blue gets incorporated into it, right? So more and more blue gets incorporated, and as it reaches blue, the or 1, T is equal to 1, it is more of blue, and here you'll have it as blue, right? So this is when you're trying to vary T across 0 and 1, right? This is the kind of variations in the pixel intensities that you will be getting, right? Now, mathematically, how you can formulate that is what is shown over here, okay? So let me, assume that the percentage of blue, okay, to B. So what we are doing is here the weights that you're taking is basically you're taking the ratio of the lengths. Okay, so let me just discuss this equation and then we'll go. In this equation, this should be tx2 over here and this should be tx1. Okay. Okay. So in this equation, let's take it as you want to find what is the value at t. I can represent that as equal to t x2 plus 1 minus t x1. Now to understand what that means, let's say I'm taking t is equal to 0 over here. So if I take t is equal to 0, this terms gets cancelled off and what I have is x1. So I'll get t is equal to x1, which is the same as discussed earlier. If you have x1 here and x2 here, okay, the value of t ranges from 0 to 1. If I'm giving t is equal to 0, I should be getting x1. And if I'm giving t is equal to 1, I should get x2 and this term gets cancelled off. Right, so t is equal to 1, I should get x2 over here. And for any other values of t that I'm considering, accordingly, the weight, okay, that is how much of red and blue is mixed, okay, that weight would be determined by t, okay, the percentage of blue will be t, and the percentage of red which is taken would be 1 minus t. Okay, so blue percent is taken as t, percent red is taken as 1 minus t. Okay, so how do we come up with this t and 1 minus t? Basically what you're doing is, okay, you're just finding out what is the length of the blue segment divided by the total length, that would give me the percentage blue, and the percent red is basically taking the length of the red segment divided by the total length, or basically you're taking the ratio of lengths as the weights. Okay, so this is nothing but a weighted average. This is an interpolation where you take a weighted average and the weights that we are considering here is the ratio of lengths. Okay, and this one, as I said, it is for a 1D image. 1D image in the sense, if you have only rows, okay, if it is a row vector, or if you have only columns, if it's a column vector, in that case you can just go with a ratio of lengths. So what if it is, for an actually image, what you have is, it is a 2D image, right? It's not just one day, it's a 2D image. So if you have a 2D image, then how do you do this interpolation? Okay, so to understand that, what we do is, so let's say you have, three pixels over here, which is given by x1, x2, and x3. Okay, and the values corresponding to these pixels, in x1 the value corresponding is red, in x2 the value corresponding is green, and in x3 the value corresponding is blue. Okay, so what are the intensities of these three pixels over here, and you want to find out, or you want to interpolate that, okay, to find a value for the pixel which is present over here at p. Okay, so here what you do is, instead of taking a ratio, so here also you take a weighted average, okay, but instead of taking these weights, in the previous case we took it as a ratio of lengths, right? So instead of lengths, in the 2D case, what we do is, these weights are taken basically as a ratio of areas. Okay, you try to calculate how much is the area which is present for each of the colors, red, green, and blue, and the weights are expressed with respect to the areas. Okay, so same thing is shown over here, how it is done. Okay, so as I said, we take the ratio of areas. Now what that means is, let's say you have a pixel over here. If you have a pixel over here, I can divide this triangle this way, okay, where this gives me, this smaller subtriangle gives me what is the area of the blue, percentage blue. Okay, this area gives me the percentage green, and this area over here gives me the percentage red. Okay, and if you're changing the position of this p, throughout, right? As you change the position of P, the percentage of blue, red, and green that gets added in the average, okay, would keep changing. The weights of these colors keep changing. Like for example, let's say the point P, okay, it is moving towards red. So if it is, let's say, if the value is at, if P is at this position red itself, okay, then what happens is, my whole triangle now is just red, so the value is red, as we see in the figure. Now, let's say if it's a little below red, as you see in this figure over here, what happens is it is, if you just without these triangles, if you're simply thinking also, you'll understand that the closer the point is towards the red, it would have more of percentage of red which is present, as compared to green and blue, which is much more further away. Okay, so the same thing is depicted over here also. When you have the point over here, you can divide this triangle into subtriangles this way, where you see that a major portion or a major contribution is done by the red color, okay, and a little bit of blue and green hue is also mixed together, or they in the weights, more weight is given to the red hue, okay, as compared to the green and the blue hue, and then the corresponding average value, or the interpolated pixel intensity value, is calculated. So mathematically, this is how we can, try to express this. That is, as I said earlier, we are taking the ratio of the areas. Okay. So when you're taking the ratio of the areas, the percentage red, I can take the ratio as area of red triangle. Okay. That is this particular red triangle A1 divided by the total area. So let's say the total area is given by A. So that is the same as written here. Percentage red is A1 by A, and let's say your, you can denote that using another variable, say lambda1. Okay. So similarly, you can find what is the percentage green by taking the ratio of the areas, and that would give me A2 by A. Percentage of blue with respect to the ratio of areas would give me A3 by A. Okay, as you see here, A3, what is the contribution by blue, and divided by the total. Okay, so this would be the percentage of red, green, and blue, which would be available, or which is actually interpolated into this particular pixel intensity value. And the more the percentage of each of these, that means the more the area which is present under these, the more would be the percentage, and the more this particular pixel intensity value, the more it will move towards that particular hue. Okay, so let's say in the mathematical form, how we can express this is, I can write the value at P, okay, is equal to A1x1 plus A2x2 plus A3x3 divided by A. Okay, so that is basically you're taking the ratio of the areas as the weights for x1, x2, and x3, and all of them, that is averaged together to find the particular value at this interpolated point. Okay, so this kind of an approach is what you call as the barycentric interpolation. Okay, it is also known as convex combination. It is also known as a fine linear extension. These are all different terms which are used for the same registration, or same interpolation technique. Okay, so now let us see how we can, use this concept of barycentric interpolation to understand how registration is done for deformable objects. Okay, so for that, what we are doing is we are going to discuss about an approach which is called as active appearance models. Okay, so active appearance models, it is very popular in in applications where you have face detection, face recognition, or emotion recognition, or trying to deform the face images to create different emotions, etc. It's not just the face, but it is more popularly, it has been worked on face images, but you do have active appearance models which are used for other deformable objects also. Okay, so we'll try to understand how these active appearance models work first, okay, with respect to these face images. So for that, let me just take this particular image which is shown. So let's say I have the image of a person's face, okay, who is smiling. Okay, so this particular image, it is smiling, and what I do is I kind of identify reference points over here. Okay, so reference points, or it's also called as landmarks, okay, are usually points which are, of interest to us. Like for example, along the chin, okay, or along the border of the chin, okay, and the face, and these eyebrow regions that you have here, the eye regions, the nose regions, and the lips, okay. So these are some of the landmarks or reference points that we are considering. Okay. So for each emotion, like for example, if the person is not smiling, the corresponding locations of these reference points would also change, right? So here also you'll see that the face, the cheeks, everything, okay. So that also kind of changes, okay. Or let's say the person has closed his eyes, or there is some kind of any other emotions which are present. Accordingly, all these reference points will keep changing its location or positions, right? So let us say that this is the image that you have, and these are the reference points which are present in the image. Okay, and these are relaxed points. So relaxed points in the sense, what you're trying to do here is, as an example, let's say I have an image of a smiling person, and I want to deform this image in order to create the image of a person who is, not smiling, or instead of not smiling, I can say who is in a relaxed face. Okay, so I'm trying to reduce this, smiling over here, and create an image with a relaxed emotion, or expression, right? So to go about that, what I do is I have the reference points in the particular image, and these relaxed points, these are basically my target over here. Okay, that means in the relaxed points, what I have is the landmarks, or the reference points, okay, for the relaxed face. That means if I observe over here, okay, it is no longer wider as shown over here, it's not longer smiling. Okay, this is the corresponding relaxed points which I have formulated for a relaxed emotion. What I do is these points, reference points which I have here, I try to register them with these relaxed points, which is my target. Okay, so that means from this image I want to transform it into this target set that I have. Okay, so by doing that, what I do is when I'm considering each of the landmark points and then trying to register that and trying to transform that, okay, accordingly, what I'm doing is basically an interpolation between these. That is, for example, for each pair of or for each set of three vertices, or three landmarks that I have, okay, I form triangles. So I have triangle here, I have another triangle here, I have another triangle here, and so on. So these, all these points we can consider as different triangles. Okay, it kind of forms a triangular mesh. Okay, now this triangular mesh, when I'm trying to deform it with respect to these relaxed points, that means I'm trying to find out what is the value of value corresponding to these points. So I know what are the values which are present in these two, and let's say for example this particular point comes somewhere over here. Okay, so in that case, what I do is I know what are the values at the vertices over here. Okay, I need to find out what is the pixel intensity corresponding to this. What I do is a barycentric interpolation using a ratio of areas to find out this particular new point. Like that I do for all the points which are present over there. Okay, so what by doing that, what you're doing is you're basically changing all the intensity values. Okay, and by changing those intensity values which are present, I'm also trying to give the appearance of the change in the expression which is present in the face. So by doing that, as a result, what I get is this particular image where the this input image or the source image over here has been registered or deformed with respect to this target set which is shown here. Okay, and after the interpolation, it might look something like this. So this kind of a method is called as the active appearance model. Okay, and in the active appearance model, it basically works with the texture. Okay, that means you're trying to deform the objects, okay, with respect to the texture which is present. Okay, and by doing that, we are trying to form a deformed object, okay, which is of interest to us. And how do we find out, or what the target set would be used as the guide in order to form that particular deformation. Okay. So what we'll do is we'll continue in the next class. We'll continue with active appearance models and how it can be used for image deformable image registration. We'll see that in the next class. Do you have any doubts so far? Okay, if you have no doubts, then we'll end the lecture today. Thank you.